Welcome to the deep dive. Today, we're digging into something you might think is totally settled science. The atom. The basic structure.
Right, the little nucleus, the electrons buzzing around.
Exactly. And that electrostatic barrier holding it all together, or keeping nuclei apart, seems pretty straightforward.
Uh-huh. That's the picture we all learned. Very useful, no doubt.
But what if it's not the whole story? What if that barrier, the Coulomb barrier, isn't just a simple electric fence?
What if it's something deeper, more dynamic?
Yeah, something that could maybe unlock ways to fundamentally change matter. Sounds wild, I know.
It does.
Okay, let's unpack this. We've gone through some pretty challenging research, a stack of sources proposing a radical new way of looking at atoms.
It's not just a small adjustment. It's a framework called Unified Atomic Coherence Physics, UACP for short.
And it seems to redefine everything: atomic size, stability, even hints at atomic alchemy.
That's the term some are using, yes. It sounds dramatic, but it stems from this core new concept.
Right. So, our mission today: deep dive into this UACP model. Look at the theory, the predictions, the potential applications, mind-blowing stuff, potentially.
Absolutely. We're going to explore this idea of a Coherence Discontinuity Class, the CDC.
CDC. Okay.
And this CDC, it basically reimagines that Coulomb barrier we mentioned. It's less about what it does repel things and more about what it is fundamentally.
So peeling back another layer of reality.
That's a good way to think about it.
Yeah.
Moving from seeing a static wall to understanding a dynamic balance point within these underlying fields, it's quite a shift in perspective.
Okay, so let's start with what we know, or what we think we know. The standard picture, the Coulomb barrier.
Purely electrostatic.
Like trying to push the north poles of two magnets together, that kind of repulsion.
Exactly. Positive nucleus meets positive nucleus. They repel. Creates an energy hill they have to climb to get close.
A static wall, essentially.
Right.
And its size, its height and width just depends on the charges involved.
Correct. And look, this model works incredibly well. It explains nuclear scattering, fusion in stars.
Yeah.
It's been the bedrock for decades.
No denying its success. But you're saying UACP sees this view as, what was the term, ontologically incomplete.
Right. Sounds a bit academic, maybe, but it just means the standard view describes what happens, repulsion, but not really why the barrier exists at that specific point or what it's fundamentally made of.
It treats it like a passive thing, a fixed wall.
Exactly. It doesn't really get into the underlying, let's call them coherent structures, the fields that actually give rise to both the nucleus and the electron cloud.
Okay.
If you picture figure 1 from the source material we looked at, the left side shows that classic view. A clear, fixed electrostatic hill, like a fence.
But the new model, the UACP view, is different.
Very different. It's dynamic, field-based. It brings that wall to life, so to speak.
That difference between what it does and what it is feels really key here. So let's dive into UACP itself. Unified Atomic Coherence Physics. You said it's a paradigm shift. It doesn't see the atom as just, bits and pieces, nucleus, electrons rattling around.
No, it views the atom as more interconnected, a nested resonance field system.
Nested resonance fields.
Yeah.
Okay. And it's all happening within something called the Universal Field Tensor, UFT.
Correct. The idea is that fundamental properties we take for granted, mass, charge, spin, even what makes an atom, say, carbon versus oxygen, they aren't just fixed properties of tiny little balls. They're emergent properties of coherence eigenvalue reduction.
Whoa. Okay, that's definitely a mouthful. Emergent properties of coherence eigenvalue reduction. Can you unpack that a bit? What does that mean in simpler terms?
Yeah, let's try. Think about maybe a whirlpool in water. The whirlpool isn't a separate thing. It emerges from the coordinated movement of all the water molecules, right?
Okay, I can picture that.
So UACP suggests mass, charge, spin. They aren't inherent properties of a particle. They emerge from how these fundamental coherence fields organize and interact.
Like the whirlpool is a pattern of water flow, not something in the water.
Exactly. Coherence here means a kind of perfect organization in the field. And eigenvalue reduction is basically how this big universal field localizes or condenses its coherence into stable patterns.
And those stable patterns are what we see as particles.
That's the idea. So mass isn't something a particle has. It is the result of this localized, coherent field structure. The pattern is the mass.
Okay, that whirlpool analogy helps. So UACP says atomic structure emerges from the interplay of two different modes of this coherence field.
That's right. Two fundamental modes.
And this changes how we picture electron orbitals, too. Not just fuzzy probability clouds.
It suggests both the nucleus and the electron fields are more like continuous resonance manifolds.
Continuous resonance manifolds, so not empty space with particles dotted around.
No, think of it more like a region filled with continuous vibrating interconnected fields, like complex patterns on a vibrating drumhead. The nucleus is a supercoherent knot in the field.
And the electron cloud.
It's also an extended vibrating field connected to the nuclear field. It gets rid of the idea of empty space inside atoms.
Wow. So stability isn't just attraction, it's these fields staying organized. You mentioned negentropy membranes.
Right. Think of negentropy as the opposite of entropy or disorder. These membranes are like an active organizing principle, a sort of energetic boundary that actively works to keep the whole system coherent, stable, preventing it from just dissipating.
And an active boundary, not a passive wall.
Exactly. It's self-organizing, maintaining the atom's structure through these field dynamics.
Okay, let's get into these two field modes then, the key players. First, the condensive coherence mode, or CCM. What's that like?
The CCM is the inward pull. Think intense gravity, but at the atomic scale, focused on the nucleus. It's described as high density, localized, and compressive.
Pulling everything in.
Right. Trying to achieve minimal volume, maximal coherence. It's linked to the strong and weak nuclear forces, the SU3 and SU2 interactions that bind the nucleus.
So it creates that incredibly dense core we know the nucleus is, like a tiny, powerful field vortex.
Exactly. Concentrating energy and mass right at the center.
And countering that inward pull, there's the dispersive coherence mode, DCM, the outward push.
Precisely. It's the dynamic opposite. Low density, spread out, associated with the electrons. It's expansive, tending towards maximum spatial spread.
So this is what gives the atom its volume, lets it interact chemically.
Yes, it projects the fields outward. This mode is more related to electromagnetism, the U1 interaction we associate with electrons.
So you've got this intense inward CCM pull from the nucleus and this outward DCM push from the electron domain, a constant dance.
A dynamic equilibrium. That's the heart of the atom in this picture.
And where that dance finds its balance point, that's the Coherence Discontinuity Class, the CDC.
Exactly. This is the crucial concept. It's the phase interface, the equilibrium surface where the inward pull and outward push balance perfectly.
And this CDC replaces the old idea of the Coulomb barrier being just electrostatic.
That's the proposal. It defines the barrier based on this field balance, the gradient balance in the coherence field, not just static charges repelling each other.
Okay, and figure 1, the right side, shows this. That orange ring isn't just a wall, it's this active boundary.
Precisely. It's a dynamic equilibrium point where the whole atomic structure finds its stability. And the physical interpretation here is really detailed and quite illuminating. We can break it down into zones.
Okay.
First, the nuclear zone. Deep inside, that's where the condensive mode dominates, focusing what they call vacuum curvature, creating that super dense nucleus, maximal organization, or symmetry density.
Then outside that.
Then you have the electron zone, the outer region. Here, the dispersive mode takes over, projecting the fields outwards, enabling chemical bonding and interaction.
Makes sense. But the CDC itself is the key boundary.
Yes, the interface, the CDC zone. It's described as neither purely condensive nor purely dispersive. It's a coherence modulation threshold.
Like a transition zone.
More than that, think of it like a membrane where the vibrations, the eigenmodes, from both the nuclear side and the electron side have to perfectly match up for the atom to be stable.
Ah, okay. That's why atoms have specific sizes and properties.
Exactly. Mathematically, it's like a phase discontinuity, where the field's nature flips from inward pulling to outward spreading. It is where we observe the Coulomb barrier effect.
But its origin is different, not just electromagnetism.
Right. It's ontologically defined, meaning it arises from the fundamental field structure. It balances coherence pressures, aligns the different forces, even acts as an information mediation surface encoding the atom's properties. It's the atom's active blueprint.
Wow. Okay, that's a completely different way to think about the barrier. So if the CDC defines this boundary, what does this all mean for how we understand something as basic as the atom's size? Because, we usually talk about electron clouds or the Bohr radius.
Right, so in UACP, the functional atomic size, let's call it raw, isn't just the fuzzy edge of the electron cloud or simply the Bohr radius. It's more precise. It's the radius where the CDC equilibrium sets the outer limit of stable electron localization.
So the size is basically set by where the CDC boundary forms.
Essentially, yes. We'd write it as raw, RCDC, plus DEDISP, the size of the CDC radius, RCDC, plus maybe a tiny bit more DISP, where the electron field kind of fuzzes out slightly beyond that main boundary before it loses coherence.
Okay, so atomic size isn't just random or statistical, it's ontologically predetermined. That sounds significant.
It is. It means the size is fixed by, 1, the nuclear coherence eigenvalue, how much energy mass is packed in the core, and 2, the dispersive field's ability to stay structured as it spreads out.
So the size is a necessary outcome of this field balance, not just where electrons happen to hang out.
Exactly. It's baked into the coherence dynamics. And we can actually derive this mathematically. It's quite elegant. We model the two modes, condensive inward and dispersive outward, as scalar fields that depend on radius. The condensive field, CCR, is strongest at the center and drops off quickly. The equation looks like CCR equals CC0D.
CC0 is the strength at the center, and I tells you how fast it drops off.
Exactly. So you'll see that R is the nuclear coherence decay constant, a measure of how concentrated that inward pull is.
Got it. And the dispersive field.
The dispersive field, CDR, does the opposite. It's weak near the nucleus and grows outwards. Its equation is CD0 1ER.
So CD0 is its maximum outward strength, and back is how quickly it grows.
Correct. HEO is the electron coherence rise constant, how readily the electron field spreads.
And the balance point, the CDC, is where their rates of change cancel out.
Precisely. The equilibrium condition is where the sum of their gradients, how steeply they're changing with radius, is 0. dCCdr plus dCdr equals 0 right at the CDC radius, RCDC.
Okay, so if you do the calculus, differentiate those equations, what does that tell you about the relationship between those alpha and beta constants and the C0s?
Well, when you differentiate CCR, you get OGC0ER, and for CDR, you get OCD0ER. Notice the different signs reflecting the opposing directions.
Inward versus outward.
Right. Setting their sum to 0 at RCDC and accounting for the opposing nature, the balance equation becomes a CC0E, RCDC, RCD0E, RCDC.
That equation captures the exact point where the inward pull rate equals the outward push rate.
Exactly. That's the mathematical heart of the CDC boundary.
And from that equation, you can actually solve for RCDC, the radius itself. That defines the functional size.
Yes. If you rearrange that equation, take the natural logarithm, you get clear solution. RCDC, L being EC0, EC0.
Wow, so the location of the barrier, the atom's functional edge, is mathematically determined by these fundamental coherence parameters.
Exactly. It's not arbitrary. And we can define a key ratio from this, the atomic coherence constant bill, which is basically EC0, BC0. It simplifies things and captures the balance for a given atom.
Okay, here's the big test then. Can this new framework, with its coherence modes and CDC radius, derive this way? Can it actually reproduce something as fundamental as the Bohr radius for hydrogen?
Yes, this is a critical check, and the answer is remarkably yes.
Really? How does that work?
If you map the terms from our coherence model onto the terms from standard quantum mechanics for hydrogen, you find a direct correspondence.
Okay.
The condensive term, related to A in the condensive eigenvalue wake, maps directly to the Coulomb attraction key 2, the electrostatic pull.
Right.
And the dispersive term, related to and the dispersive eigenvalue wall, maps perfectly to the quantum kinetic pressure term, 2m42. That accounts for the electron's tendency to spread out.
So you're subbing in the standard physics terms for attraction and electron spreading into your coherence balance equation.
Exactly.
And what pops out for the radius R, does it actually give the Bohr radius formula?
It absolutely does. When you make those substitutions, R simplifies beautifully to RA key 2.
And that is A0, the Bohr radius.
Precisely. It shows the Bohr radius isn't just some number. It emerges naturally from this deeper coherence balance. UACP provides a field-theoretic foundation for it.
It connects the new theory right back to established quantum mechanics.
Yes, and it lines up perfectly with things like the virial theorem, too, which relates kinetic and potential energy for stable systems. The balance just works out.
That's genuinely compelling. It means atomic size isn't just a fuzzy boundary or statistical average. It's, like you said, necessitated by the balance of two opposing coherence gradients. The Coulomb barrier's position becomes a coherence-determined structural inevitability.
It suggests the size is baked into the fundamental field interactions.
No, usually when we say atomic size, we just think of one number, but you're saying UACP sees it as having layers, different scales.
Exactly. It's not just one size fits all. There's a hierarchy, which gives a much richer picture. This is where it gets really interesting.
Okay, lay it out for us. What are these different scales?
We identify 3 distinct radial scales. First, the nuclear matter radius. This is the actual physical size of the nucleus itself, the dense core, measured in femtometers, 10, 15 meters. Incredibly tiny.
The actual stuff of the nucleus, and that's the source of the inward pull, the CCM.
Right. It's the source region for that condensive gradient. Think super dense, almost point-like core.
Okay, scale number 1. What's next?
Second, there's the condensive gradient extent, Alchemy.
Yeah.
This isn't the matter itself, but how far the influence of that nuclear coherence field ascends significantly. It's bigger than Reinach, maybe 14 to 12 meters.
So still tiny, but the field's reach is a bit bigger than the physical nucleus.
Yes. It's the zone where the nuclear forces, the SU3, SU2 coherence, still strongly dominate the local environment, like a powerful, fading field aura around the core.
Still way smaller than what we think of as the whole atom, though. So the third scale must be the big one.
Exactly. Third, and most critical for chemistry interactions, is the CDC location, our CDC. This is that functional boundary where the inward and outward gradients balance. RC condensive, Fellensdidefeest.
In this radius, RCDC is what we typically measure as the atomic radius, around 10 meters angstroms.
Precisely. It coincides with the experimentally observed atomic radius. It's the operational boundary for chemical, identity, stability, interactions. It's a functional equilibrium surface.
It's where the electron's field volume gets locked in by that balance.
That's a great way to put it. It fixes the scale for chemical behavior.
So we have this clear hierarchy. Reinach is way smaller than RC, which is way, way smaller than RCDC, which is basically radom. Like 5 orders of magnitude different.
Yes, from femtometers for the nucleus out to angstroms for the CDC boundary. A huge range within one atom.
Can you visualize that, like the diagram mentioned in the sources?
Absolutely. Imagine that nuclear condensive CDC diagram. Tiny dark red dot, nuclear matter, or yogic, femtometer scale.
Yep.
Slightly larger light red zone, condensive gradient extent, RC, the nuclear field's immediate influence zone. Much, much further out, an orange dashed ring. CDC boundary, RCDC, angstrom scale. This is the crucial balance point. Surrounding that, a light blue halo, the dispersive electron field domain extending outwards.
So that visual really drives home that the functional size, the size relevant for chemistry, is set way out at that CDC ring, not near the tiny nucleus.
Exactly. For you, the listener, it means the atom's interaction size isn't its dense core, but this much larger dynamic field boundary.
And this separation has big consequences, right? Because these different scales follow different rules, like nuclear size scales with mass number, but the CDC depends on these coherence eigenvalues.
That's the crucial point. Reinach scales roughly as A13, but RC and, more importantly, RCDC depend on Look and Lud.
Which leads to
the possibility of atomic size tuning. If you could somehow tweak UC or Lud, maybe with external fields,
you could shift the CDC location, change the atom's effective size, without changing the nucleus itself.
That's the truly mind-bending implication.
Yeah.
It suggests atomic radii might not be fixed constants of nature, but potentially malleable parameters.
Wow. Imagine being able to resize atoms, the possibilities for materials science, catalysis,
Right.
controlling matter at that fundamental level. It's almost unbelievable.
So building on that, if atomic size R is determined by this coherence balance at the CDC, we can actually work backwards.
Use the size we measure to figure out something about those underlying fields.
Exactly. We defined that coherence ratio, R dislic, and we know the radius is related ROK, where K is some scale factor. We can invert this.
Okay.
We can use the observed atomic size, Rob, to reverse engineer this coherence ratio. And this is directly related to that atomic coherence constant K we touched on earlier, which reflects the relative steepness of the two fields at the boundary.
So measured size gives us insight into the hidden field dynamics. That's powerful. But how do you pin down that scale factor, K? How do you calibrate it reliably against real data?
Good question. There are 3 main ways proposed to calibrate K, connecting theory to experiment. First, hydrogen calibration. Hey, hydrogen is the simplest, our natural baseline. We set K equal to the Bohr radius, A0, which we know very precisely. Then rho for hydrogen is just its observed radius divided by A0. Simple and accurate starting point.
Makes sense. What about more complex atoms?
For those, we use screened hydrogenic calibration. B, we bring in the effective nuclear charge, Zeph, which accounts for electron shielding. Here is related to N2 Zeph or Rob Zeph A0. This lets us use existing data tables for many elements.
Okay, using known atomic properties, is there a more comprehensive way?
Yes, the third method. Data-driven calibration. C, this is more sophisticated. We treat K as a global constant to be fitted statistically. We build a model where Rob's K, but itself is predicted, using a bunch of known atomic properties, principal quantum number N, Zeph, ionization energy, I, polarizability.
So you're using a whole range of data to find the best fit for K and understand how rho depends on these other factors.
Exactly. It gives the best overall picture, linking the coherence ratio to a wide array of empirical observations.
That really grounds the theory in experimental reality. Let's make it even more concrete. Can you walk us through the carbon-12 example calculation? How do these numbers play out?
Sure. For carbon-12, its nuclear radius, Rn, is tiny, about 2.47 femtometers, or 2.47 by 10,000 angstroms. Its nuclear radius, Rn, is tiny. Its atomic radius, Ra, for chemistry, is about 0.70 angstroms. Much bigger.
Okay.
We can estimate the CDC location, our CDC, using a geometric mean, our CDC, and Rn Ra, plugging in the numbers.
Square root of tiny number times big number.
Right. It gives our CDCA 4.16 or 10.3 angstroms, about 4 picometers. Still small, but way bigger than the nucleus.
Got it. So the CDC is nestled between the nuclear and atomic scales. Now, how do you get high from that?
We use the formula Kie.
Yeah.
Re RCDC. Assuming the electron extent Re is roughly Ra 0.70A, we plug in the values.
0.70 minus 0.00416 divided by 0.00416.
Exactly. It comes into carry a 167.8. It's called 168.
Okay, take as about 168 for carbon. What does that number actually tell us physically? Why is that significant?
Carry of 168 means the condensive decay rate, the inward pole steepness related to ARI, is about 168 times steeper than the dispersive growth rate. The outward pushes steepness related to ARI right at that CDC boundary.
Wow, a huge difference in how fast those fields change right there.
Yes, and this massive asymmetry explains why the nucleus seems almost point-like from the perspective of the outer electrons. Its direct field influence drops off incredibly fast.
And why the electron cloud is so much bigger.
Exactly. The dispersive field whims in terms of spatial extent. It also implies that the boundary is very sensitive. Small changes in the underlying air or air could significantly impact things like quantum tunneling rates. It highlights the dominance of the expansive electron field in defining the atom's interactive size, despite the nucleus's intense core.
That gives real physical intuition to that number. Now, you also mentioned a more complex model using multiple atomic features to predict K. What did that regression analysis show?
Right, a preliminary multi-feature regression was done. The model looked like this. K of 337.8 plus 1.13 ZO, that's 24.0 N Kia, 6.0 I plus 0.95 up P.
Okay, so Z is atomic number, N is the outer shell, Zeph is effective charge, I is ionization energy, I is polarizability.
Correct, all standard atomic properties.
And how well did this model work? Did it predict K accurately?
It actually did surprisingly well for a first pass. It got an R-squared value of 0.868.
R squared, closer to 1 is better, right?
Yeah.
So 0.868 means it explains about 87% of the variation in K. That's pretty good.
Very good. It shows a strong relationship between K and these fundamental properties. If you plotted observed versus predicted K, the points would fall very close to a straight line. The source also had charts showing which features were most important.
So looking at those coefficients in the equation, what were the main takeaways? What drives K the most?
The biggest impacts came from the negative terms, especially for N, the principal quantum number, and Zeph, effective nuclear charge.
So electrons in higher shells, bigger N, or electrons feeling a stronger effective pull, bigger Zeph, lead to a lower Kia.
Exactly. It suggests that a more spread out or more tightly bound electron configuration reduces that coherence constant value, shifting the balance.
Interesting. And the positive terms, atomic number Z and polarizability app.
They tend to increase Kia. So more protons, electrons generally, and more easily deformable electron clouds correlate with a higher Kia. Ionization energy, I had a negative effect, consistent with tightly bound electrons, reducing the dispersive aspect.
So the bottom line from this analysis.
The key conclusion is that Kia seems predominantly governed by two main things: the outer electron shell level N and the effective nuclear charge. This really reinforces the core idea. The Coulomb boundary isn't just electrostatic, it's this dynamic phase interface where condensive and dispersive gradients balance, and that balance is intimately tied to the atom's electronic structure.
Okay, this is where my mind starts to bend a little. Because if the CDC is the Coulomb barrier, and its location depends on these coherence gradients, does that mean we could potentially change the barrier?
That's precisely the most profound implication. If the barrier is the CDC interface, its height and width aren't fixed. They're functions of those gradient slopes, a Kina, essentially.
So barrier modulation, we could tweak, look, or up somehow.
That's the theoretical possibility. Altering those coherence eigenvalues could effectively shift the barrier, make it easier or harder to penetrate, without directly messing with the electrostatic forces in the usual sense.
Which gives that unified view you mentioned,
Yeah.
connecting atomic size directly to nuclear reaction thresholds.
Yes, it links chemical scale geometry, atom size, with nuclear scale interactions, tunneling probability, through this single field principle. It bridges two traditionally separate domains of physics.
And that bridge leads directly to this idea of atomic alchemy, controlled transmutation, making one element into another.
It sounds fantastical, but the logic follows from the CDC model. If the CDC is the barrier, modifying it provides a direct route to controlling nuclear tunneling rates.
How?
Remember quantum tunneling. Particles can sneak through barriers they don't have the energy to climb over. By selectively reducing RCDC, making that coherence barrier effectively narrower or lower,
You increase the chance they'll tunnel through.
exactly, you boost the probability of nuclear penetration, even at much lower kinetic energies than conventional methods require. No need for the extreme conditions of fusion reactors or the chain reactions of fission.
Okay, so figure 3 in the sources illustrates this, showing the CDC shifting inward.
Yes. The left panel shows the normal CDC position, black dashed line. The right panel shows it shifted inward, green dashed line. The shift comes from flattening those coherence gradients, making the barrier effectively thinner and lower.
Resulting in easier tunneling. So how might we actually do that? How could we flatten those gradients?
Several methods are proposed. One is coherence field modulation. Using precisely tuned external fields, maybe resonant electromagnetic fields, maybe even more exotic scalar fields, to directly influence Fuke, or IDS, like tuning the atom with the right frequency of light or field.
Okay.
Another is electron coherence compression, using extreme conditions like high-pressure, super-strong magnetic fields or tailored plasmas to physically squeeze the electron cloud, the dispersive field, closer to the nucleus.
Forcing the outer boundary inward.
Right. And a third way is isotope tuning. Different isotopes of the same element have slightly different nuclear structures, which might mean they naturally have slightly different nuclear ratios. We could select isotopes that are already more amenable to tunneling or respond better to field modulation.
And the potential applications. They're huge. Low-energy nuclear reactions, LANR, getting nuclear reactions without needing star temperatures.
Potentially much cleaner and more controllable energy release.
Isotope conversion, making specific isotopes on demand for medicine or industry.
Precisely. A more targeted way than current methods.
And waste transmutation, turning dangerous, long-lived nuclear waste into stable stuff. That would be revolutionary.
It offers a conceptually new path, distinct from fusion or fission, for potentially addressing some of our biggest energy and waste challenges. And the implications go even further than transmutation. Think about atomic and molecular engineering, if you can resize atoms.
You could fine-tune chemical reactions, design perfect catalysts, create materials that adapt their properties on demand.
Exactly. Field-controlled catalysts, variable-size atoms for adaptive metamaterials. It opens entirely new design spaces.
What about isotope-dependent chemistry?
The model predicts subtle differences in reaction rates based on isotope-specific Eck shifts. This could explain known anomalies and maybe lead to new ways to separate isotopes.
And precision metrology, using atoms to sense fundamental constants.
If Ratum K, then measuring Ratum incredibly precisely could let us track tiny variations in fundamental constants by monitoring the CDC location. Could lead to even better atomic clocks.
Materials science changing lattice spacing without changing the atoms. Designing materials from the ground up based on field control.
Yes, tuning material properties dynamically. And it could improve our understanding of nuclear electronic coupling, explaining things like hyperfine splitting or the meonic atom puzzles better than current models.
And theoretically, it acts as a bridge between this new coherence field idea and standard quantum mechanics, which is vital for acceptance.
Right. It connects to what we already know, providing testable links.
Okay, this all sounds incredibly promising, even revolutionary, but big claims require big proof. How do you actually test something like this? How do you experimentally verify the existence and tunability of the CDC?
That is absolutely the critical next step. The proposals outline several very specific, high-precision experiments designed to look for unambiguous CDC signatures. They're challenging, no doubt.
Give us some examples.
Okay. One is coherent field tuning of atomic radius, neutral gas. Take a noble gas, like argon, in a controlled environment. Apply very specific coherent laser fields, not strong enough to ionize, but enough to gently perturb the coherence fields, AC Stark regime. Then look for tiny shifts in Rydberg spectral lines, or changes in how often the atoms collide.
And the CDC signature.
A systematic, reversible change in the inferred atomic radius that scales with the coherence of the applied field, consistent with AUCO.
Okay, what else? You mentioned a hero experiment.
Yes, isotopic series spectroscopy. This compares spectral lines from different isotopes of the same element, like lithium-6 versus lithium-7, with extreme precision. Standard physics predicts shifts, but there are tiny discrepancies.
And the CDC prediction?
It predicts an additional small systematic shift that correlates with the neutron number, arising from subtle changes in nuclear coherence due to the different nucleus. This could directly explain those lingering discrepancies in a way conventional models struggle to. That's why it's a strong candidate.
Interesting. What other approach?
There's muonic versus electronic atoms. Replace an atom's electron with a much heavier muon, which orbits way closer to the nucleus. The muon should feel a different Lick balance because it probes deeper. Comparing muonic hydrogen energy levels to regular hydrogen could reveal this difference, maybe even solving the proton radius puzzle.
Probing the infield more directly.
Exactly. Then there's ultra-low temp ion traps. Trap single ions, cool them way down, then subtly vary the coherence of the trapping fields. Look for tiny shifts in the ion's clock frequency that depend specifically on field coherence and not just intensity.
Showing that organization matters, not just power.
Right. And finally, anti-AFM single atom manipulation. Use those incredibly sensitive microscopes to look at individual atoms on a surface. Apply localized coherent fields and see if you can directly measure a tiny change in the atom's apparent size or how it bonds, again, driven by coherence.
These experiments sound incredibly demanding. Cryogenic temperatures, ultra-high vacuum, exquisite field control.
They absolutely are. It requires state-of-the-art techniques. Yeah. But the potential payoff, confirming a fundamental shift in our understanding of atoms, justifies the effort.
Yeah.
And if these experiments work, if they're replicated, it really would meet the criteria for a Kuhnian paradigm shift.
Oh, so?
Well, first, it reframes a settled area, atomic size and nuclear coupling. UACP offers a new foundation. Second, it bridges the usually separate domains of nuclear and atomic molecular physics with a unified field boundary. Third, it's predictive and testable that Rotom-Lick relation is concrete and falsifiable. And fourth, it explains anomalies, those nagging discrepancies in isotope shifts, muonic atoms, etc., might find a coherent explanation.
So, potentially huge. But what about the ultimate recognition, like a Nobel Prize? What's the bar for something like the CDC model? Beautiful ideas aren't enough, right?
Absolutely not. For Nobel recognition, the bar is incredibly high. You need, first, independent replication. Multiple labs, different methods, all confirming the CDC effects, non-negotiable. Second, a clear break from conventional explanations. It has to be shown, convincingly, that these effects cannot be explained by tweaking existing QED or DFT models. It must be fundamentally new.
Can't be just a known effect in disguise.
Right. And third, a simple empirical hook. The physics community needs a clear, relatively accessible prediction they can test. That isotope spectroscopy experiment seems like the best bet for that initial hook.
So given those hurdles, what's the game plan? How do you strategically take this from a compelling theory to something accepted by the mainstream, potentially winning that highest honor?
There's a clear roadmap outlined. First, hero experiment selection. Focus effort on that high-resolution isotope spectroscopy test. Get key labs working on it.
Laser focused.
Second, mainstream mathematical formulation. Translate the core ideas, especially Reta-Millipic, into the familiar language of QED and field theory. Make it accessible.
Seek their length.
Third, strategic dissemination. Quietly approach top experimental groups first, then publish a short, high-impact letter, PRL, with the key prediction method, present clearly at major conferences, leading with the testable prediction.
Build momentum carefully.
And fourth, crucially, data-first publication. Once solid replicated data exists, publish the experimental results and the CDC interpretation together in a top journal, Nature Physics, PRL. Then follow up with detailed theoretical papers. The empirical proof has to come first for a paradigm shift to take hold. Hashtag and outro.
Wow, what a journey. We've gone from the atom we thought we knew, with its simple electrostatic barrier, to this complex, dynamic picture based on unified atomic coherence physics. This idea of the Coherence Discontinuity Class, the CDC, defining the barrier through a balance of fields. It's profound.
It really reframes how we think about atomic size and stability.
And the implications. Potentially tuning atomic size, enabling low-energy nuclear reactions, this atomic alchemy. It's almost hard to grasp the possibilities. So what does this all mean for you listening in? How should this change how you see the world?
Well, if this framework proves correct, if the experiments bear it out, It paints a picture of the universe where the fundamental properties of matter aren't quite so fixed. Atoms aren't just static building blocks. They're dynamic equilibria of these underlying coherence fields.
Fields that might be tunable, controllable.
Potentially, yes, in ways we're only beginning to imagine. Manipulating matter not just by heating it or smashing it, but by subtly adjusting its internal coherence. It suggests a reality that's maybe more interconnected, more dynamic, and perhaps even more malleable than we ever thought possible.
A universe buzzing with interconnected fields, where even the atom's edge is an active dance. It definitely gives you something to think about. It challenges assumptions and opens up entirely new avenues. We hope you'll keep exploring these frontiers with us. Thanks for joining this deep dive.